Okay, so variable frequency drives. This is one of the most phenomenally complex topics that you'll ever cover. Fortunately, all you need to worry about is on your handout bundle, the block diagram, which I believe is on page 3. If I have a quick run through of some of the basic concepts, if we take an AC motor, this is our supply current. So here's the supply current going to the motor. Then to make that motor run at full speed, then all of this current is delivered to the motor. Okay, so that makes it run at full speed. And that would be true for any motor. So if we take a different approach, and if we use electronics to reduce the amount of current that's flowing to a motor, then hopefully we can slow it down. So if we were to use something like a Thyristor, which we can turn on and off at a convenient time, we may get something like this. So we turn it on, turn it off, then nothing. Then we turn it on again, turn it off, then nothing. So in this particular circuit, which will work for some types of motor, like a universal motor, and it would work in a lamp dimmer circuit, then instead of delivering all of that current, we're only delivering about half of it. So in terms of motor speed, we've made it go a lot slower. So this still isn't ideal. So let's take a very slightly different approach. Still working on using electronics and using thyristors. If we were to send a little bit of current, turn it off, a little bit of current, turn it off, a little bit of current, turn it off. And then for the other half cycle, do the same again, turn it on, turn it off, nothing, turn it on, turn it off, nothing, turn it on, turn it off. Then suddenly it looks very different, but what we have is still a sine wave. We've still got our basic sinusoidal shape there. Although the current we're now delivering is this, 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 this. So we're delivering a lot less current. So this is now one step closer to where we need to be for true variable frequency drives, because all we're doing at the moment is we're keeping the frequency the same, but we're delivering different amounts of current. So let's take that a little bit further and examine this a little bit more. Right, so in your handout bundle, you'll have reference to something called dual rail supply. And I've tried to explain that here. If we were to take two 12-volt batteries and we connect them together, like so, then where they meet, we're going to say this point here is 0 volts. If you like, it's a reference point. At the other end up here, this, with reference to 0, this is plus 12 volts. And at the bottom end, with reference to this is minus 12 volts. So you might want to just play that through again in your own time and have a think about what I've just done. But I've created two rails, a positive rail and a negative rail, and we have 0 volts sitting in the middle. So let's move on to the block diagram which you have on your handout, and this is a simplified version of it. This is going to be the basic system. We're going to take a 3-phase supply. So L1, L2, L3, brown, black, grey, however you want to describe it, they're going to go into a three-phase rectifier. The three-phase rectifier will produce something like this, but with much bigger voltages. So we're going to have a system that will have, and I've arbitrarily gone for 300 volts, 0 volts, and minus 300 volts. So at this point here, our rectifier has now produced this three-phase supply to a DC supply. And this is what we want. The electronics, the control circuitry in here, will consist of a range of circuits, but one of the main ones we want to think about is one's using a thyristor. The thyristor is going to deliver a series of pulses. So it's going to go something like this. The output at this point, let me go to a different colour, the output at this point here is going to be a series of positive going pulses. So a series of positive going pulses, 0 to 300 volts. We then pull in a series of negative going pulses, 0 to minus 300 volts, and we then get another series of positive going pulses. So you might think this is strange, but we've got a series of positive DC pulses, negative DC pulses, positive. But as far as the motor is concerned, the motor will see this. A bit wonky, but hopefully you get the idea. Even though it looks very different, the motor still thinks it's receiving a sine wave. And that is crucial. So at this point in time, all we're delivering is a fixed speed. So on my next sheet, and it'll be the final sheet of your handout bundle, we just need to take this to show how we actually change the speed, and it's to do with these pulses. Okay then, so I've chosen an operating frequency of something like 60 Hertz, and I've done that deliberately. The reason will become apparent as we do the following diagrams. So we're going to use thyristors to send pulses to our induction motor. And what we'll do is we'll send something like this. Oops. And then a negative going pulse. Then another one. Hopefully you get the idea. So we're just sending a big fat DC pulse. Sheet of paper's moving. Okay, so that's what we're going to send from our control unit, from the electronics. The motor doesn't realise it's receiving a square wave. The motor thinks it's got something like this. And I'll try and draw it. Oops, a bit wonky. So we're sending a string of DC pulses, the red, but the motor doesn't care one bit. The motor just thinks, oh, this is positive going, negative going, positive going, negative going, just like a sine wave, and it will run at its normal rated speed. What I've done on the next line down is I'm going to slow the motor down, and this is where the electronics come in. We change the duration of the pulses. If we slow them down, then we'll change the speed of the motor, because motor speed is controlled by frequency. So let me try and give you that as an example. So we're going to send some positive pulses. Then some negative pulses. Oops. And then positive pulses again. I'm sure you get the idea. I am rushing this. And again, what's going to happen now is the motor hasn't got a clue that it's receiving square waves. It's going to see something like this. Oh, not very well drawn at all, sorry. There we go. So lower in amplitude, but the frequency, if you look at this, we have halved the frequency in this instance. That's why I chose 60 Hertz, so I could do 60, 30 and 15. So this is now going to be 30 Hertz. So we've slowed the motor down by changing the duration and number of pulses. Final step, let's slow it down further. So I'm not going to spend my time doing a lot of clever pulses, but we're going to send a whole string of narrow pulses like so. And then we're going to change the polarity and we're going to send a whole string, same number of pulses on the negative half cycle. And what the motor will now see is something like this. So still a sine wave, lower amplitude, slower. It's got a slower frequency. So we've slowed the motor right down. So before I finish this, throughout your handout bundle I have expressed that this is a shortcut. I've taken a lot of shortcuts. Motor speed control is a phenomenally complex topic, and I've given you more than enough that you need at this level. The key you need at this level is the block diagram and to be able to explain it.